In our final two lessons, we'll be looking at the idea of an annuity. Now, an annuity is different than the compound and simple interest equations that we had in the previous lessons. In those lessons, we were investing one sum of money and waiting for it to grow over time. In real life, people don't always do investments like that because after they get their weekly paychecks or monthly paychecks, they're able to invest a little bit of money each month or maybe each week, something like that. That's what an annuity is. An annuity is a series of payments made at regular intervals. So you make a payment every month, every day, every week, anything like that. Now, we'll be assuming what are called simple ordinary annuities. A simple annuity is when the payments occur at the same rate as the compounding period. So if the interest is compounded weekly, the payments will also be weekly. So those two intervals will match up. Also, an ordinary annuity is when payments are made at the end of each interval. So at the end of each month, the end of each year, anything like that. Now, here's how an annuity will work. And I'm going to be showing you visually, and later on we'll be figuring out what the formula is. So you invest $100 at the end of each month for a year. How much will you have in total at 0.48 compounded monthly? Now, the first thing I can do is, just like we did before, is figure out what my interest rate is. So I is 0.048 divided by 12. My I value would be 0.004. So we're still going to compound our interest like normal. So now I'm going to visually show you what's going to be happening with an annuity. Now, we're going to be starting at month number 0. So this is kind of like the beginning of the year, but we're not investing any money until the end of January. So at the end of January, at the end of month 1, we're going to be depositing $100. At the end of month number 2, which is February, we're also going to be depositing $100. Now, this is going to keep continuing on, so I'm going to place this break here. So the final 2 months will be October, November, and December. And again, in each of those months, we're going to be depositing $100. Now, here's the thing. All of these sums of $100 will be earning interest. So when you invest this $100 in January, it earns interest throughout the year. Same thing with the $100 in February, it earns interest. The only one that does not earn interest is this very last one. It's being deposited at the end of December, so it's not going to earn any interest that year. But the one in November will be earning interest, and it's only going to earn interest for 1 month. So it'll be multiplied by 1.004. The next one, or the previous one in October, now it's going to earn interest at the end of November and at the end of December. So it earns interest for 2 months. Now, if we were to go back one more payment, so the September payment, it would earn interest in 3 months. Now, going back to February and January, how many months will both of these earn interest? Well, you can count on your fingers, or we can just think of it logically now. There are 12 months in a year, but this January payment, it doesn't actually earn any interest in January because the payment was right at the very end of the month. So the number of months it earns interest is 11. And for February, that means it earns interest for 1 less month, which is 10. Now, what we're going to have to do here to figure out how much money you have in total, we're going to have to add up all of these. And this could get a little bit tedious. I mean, we're going to have 12 different deposits that we've added up, and 11 of them are earning interest. So we're going to develop some sort of formula to make a little shortcut. It turns out that we can use one of the ideas that we've already talked about in sequences and series. Now, I'm going to be counting out these sums backwards. Now, the first, in our example here, the last term was 100. That was the amount of the payment, which we're going to be using a capital R to denote that. Now, the next term before that is equal to R times, and it earns interest once, so 1 plus I. The term previous to that, again, is R, so the payments are the same all the time, but then it was earning interest twice, so that'll be 1 plus I squared. Now, it will go on and on like this until we get to a certain point. So the second last payment was earning interest for, now if you take a look at, we have 10 as our exponent here, but there were 12 months in the year. So that 1 plus I will have an exponent of n minus 2 because it receives interest for 2 less months than the number of months in total. And the very last payment, again, of R is going to be earning interest for the longest amount of time, but that amount of time is n minus 1 months because, again, it doesn't earn any interest for that first month. Now, you're looking at this, and this may look familiar. This is actually a geometric series. So our first term is R, and our common ratio is 1 plus I, because that's what we're multiplying each time, 1 plus I, because each additional, or each payment is earning interest one additional time as we go through. So for the geometric series, our A value is R, and our common ratio, lowercase r, is actually 1 plus I. So what I'm going to do, I'm going to write out the geometric series equation, but substituting in these two new values. And what we're going to get is a new equation to figure out an annuity. So the A value is simply R. Now for a geometric series, it's the common ratio to the power of n. So it'll be 1 plus I to the power of n, and then subtract 1. And the whole thing is divided by the common ratio, which is 1 plus I, subtract 1. Now, just looking at this right here, I can simplify the denominator a little bit. 1 plus I subtract 1 is just simply I. So this is our equation for the future value of an annuity, but we're not going to call it a sum anymore. So we're actually going to use capital FV to stand for future value is equal to, and then this is our formula. So R is what we call the regular payments. So the regular payment is how much you're paying at regular intervals. And the rest of it is exactly as we would normally do, that I is the interest rate per period, and N is the number of periods. All right, so we're going to look at a couple of examples here. And just like any of the other formulas, we're going to always substitute in whatever we know, and then we're going to solve for whatever the unknown value is. Now, if we invest $500 every 3 months, this means that my regular payment, R, is $500. Now, if it's every 3 months, if you remember, that means that we are investing quarterly, every quarter of the year. Now, it's 5.2% compounded quarterly. So as we mentioned, the compounding interval and the payment interval will be the same. So 0.052 divided by 4, because it's quarterly, will give me 0.013. And we want to know how much will you have after 10 years. Now, if 10 years are going by, remember that we're earning interest this time 4 times a year. So we get N is equal to 40. So putting together my future value formula, my R value is 500. Now 1 plus I is 1.013. That's to the power of N. Subtract 1, and then the whole thing is divided by just I, which is 0.013. A very common mistake is some people will divide by 1.03, but it is just I in the denominator. So make sure you understand that formula. So in total here, I've calculated that we will have $26,015.41 if I round it. Now, here's something interesting. This question doesn't ask for it, but how much interest do we earn along the way? Now, to figure that out, what we'll have to do is, and I'm going to use capital I again for interest earned, just like with simple interest, you have to think of how much money have we actually paid. Now, in total, we end up with $26,015.41. Now, remember that the $500, that's our regular payment, but how many times is that happening? Well, that $500 happens for 40 months. So that payment happens 40 times, so $26,015.41 subtract, this is how much we paid right here. So in total, we made interest of $6,015.41. All right, so the last question here. So I've decided that I don't really like teaching anymore. I'm saving for retirement. So I want to save $500,000 in 20 years. So I want to have $500,000 at the end of that 20 years. How much will my semi-annual deposit have to be at 9.6% compounded semi-annually? Now, the difference with this question here, we don't know what the payment is. This is what we're trying to figure out. But what we do know is the future value is going to be $500,000. Now, I'll quickly figure out that the I value, the interest rate per period, it's compounded semi-annually, so divide by 2. Now, 20 years are going by, but I'm earning interest twice per year. I'm also doing payments twice per year. N is equal to 40. So what I have to be careful of when I'm putting together the equation, this is my future value, which is what we calculated last time. But now I can solve for R. So it's kind of like the questions where we had to solve for the first term in a geometric or arithmetic sequence or series. So 1.048 to the power of n, subtract 1, and then divide by I, so 0.048. So now I can try to solve for R. Now to do that, I'll multiply the other side by 0.048, and I get a value of exactly $24,000. Now, do not round that if it doesn't work out to be a nice number. Otherwise, you're going to run into some trouble. So I'm left with R times 1.048 to the power of 40, subtract 1. So I'm not actually evaluating that there because I know it's not going to come out to a very nice number. But I can divide now both sides by 1.048 to the power of 40, subtract 1. So if I do that on both sides, that will now have R isolated for me. So this leaves me with an answer of $4,345.42 approximately. So that's how much I would have to invest every 6 months or semi-annually if I want to save $500,000 by retirement.